All right, let's take a trip, a 350-year journey to be exact, through one of the most familiar yet most mysterious concepts in all of science, gravity. We're going to look at three totally revolutionary ways of seeing it. We'll start with the idea that pretty much launched modern physics, and we'll end up right on the cutting edge of what we know today. This is really a story about how our picture of reality itself has changed over time.
Okay, so here's the game plan. First, we'll dive into the classic idea of a universal force. Then, we'll see how Einstein's happiest thought completely flipped the script. From there, we'll get into some really wild modern territory with the idea of gravity from information. And to wrap it all up, we'll bring all three perspectives together to see the big picture. So first stop on our journey, the Newtonian foundation. This is really where it all begins for physics students, right? With Sir Isaac Newton and his unbelievably powerful and honestly beautiful description of gravity.
Newton's law is probably familiar to a lot of you. It treats gravity as a straight-up force, an invisible rope, almost, that reaches out across the emptiness of space, pulling any two objects with mass toward each other. What was so incredible about this is that it unified, for the very first time, the physics of things here on Earth, like a falling apple, with the grand dance of the planets up in the heavens. But, there was this nagging question that stuck around for more than 200 years. How does this action at a distance actually work? What is this field? How does the sun, all the way over there, tell the Earth to keep orbiting it across millions of kilometers of, well, nothing? That puzzle lingered, and the answer, when it came, was a complete game changer. So let's jump into that revolution. This was the first huge paradigm shift, and it came from the mind of Albert Einstein, from a moment he later called his happiest thought. I want you to imagine you're inside a sealed box, like an elevator with no windows. You drop a ball, and it hits the floor. Now here's the question. Are you sitting still on the surface of the Earth, or are you way out in deep space in a rocket that's accelerating upwards? Einstein realized you literally could not tell. There is no experiment you could do inside that box to figure it out. And that was the thunderbolt of insight. The feeling of gravity is identical. It's physically indistinguishable from the feeling of acceleration. This amazing idea is now called the equivalence principle, and it's not just a clever thought experiment. It is the absolute bedrock of Einstein's theory of general relativity. It's the clue that suggested maybe, just maybe, gravity isn't a force at all. And this new picture is captured perfectly by the physicist John Archibald Wheeler. He said, "Space-time tells matter how to move, matter tells space-time how to curve." How great is that? It's this cosmic feedback loop. Gravity isn't some force pulling objects through space. Gravity is the shape of space and time itself. So in this new view, things with mass and energy literally bend the fabric of the universe around them. And other objects, they're not being pulled. They're just moving in the straightest possible line they can through this newly warped geometry. We call those paths geodesics. So the Earth isn't being pulled by the sun. Nope. It's just following its natural, straight-line path through a patch of space-time that has been seriously curved by the sun's immense mass. Okay, so we've gone from force to geometry. Now, let's get right to the cutting edge, because it gets even weirder. What if gravity isn't fundamental at all? Not as a force, and not even as geometry. What if it's something else entirely? Well, in 2011, the physicist Eric Verlinde published a paper with a truly mind-bending proposal. He asked, what if gravity isn't a fundamental part of nature? What if it's an emergent phenomenon, something that bubbles up from a deeper, more basic level of reality? Verlinde's idea is that gravity is an entropic force. Now, what does that mean? It means it's not a fundamental pull or push. It's a force that just appears because of a system's natural tendency to get messier, to increase its entropy. Think about a gas filling a room. There's no special expansion force pushing the molecules apart. They just spread out because there are way more ways for them to be spread out than to be huddled in a corner. It's just statistics. And Verlinde asks, what if gravity is just like that? Now, to really get a handle on this, let's use a fantastic analogy from chemistry, the elasticity of a polymer. Okay, picture a long, tangled-up polymer chain. You can grab the two ends and pull it straight. When you let go, what happens? It snaps back into a coiled-up mess. But what's the force that's actually pulling it back? It's not some charge or anything, it's entropy. There are just astronomically more ways for that chain to be randomly coiled and disordered than there are for it to be perfectly stretched out and ordered. The universe prefers disorder, so the chain is statistically driven back to that messy state. And that statistical preference shows up as a real, measurable force. So, Verlinda's theory basically scales that exact same logic up to the entire cosmos. It suggests that spacetime pushes massive objects toward each other for the same reason the Palmer snaps back, because that arrangement represents a state of higher entropy, of greater disorder. In this view, gravity isn't some deep property of matter, it's an emergent effect of thermodynamics. It's just the universe settling into its most statistically probable state. Wow, okay, we have covered a ton of ground, from the birth of classical mechanics to ideas that are still being debated today. So let's take a breath and put these three incredible views of our universe side by side. This chart really sums up our whole journey, doesn't it? For Newton, gravity is a force, this mysterious action at a distance. For Einstein, gravity is geometry, best imagined as that bowling ball warping the fabric of a trampoline. And for Verlinde, gravity is information, an entropic force that acts just like that polymer snapping back into its most disordered state. Three completely different ways of describing the exact same thing we all experience every day. And that really brings us to the biggest question of all, the real takeaway here. This journey to understand gravity, from a force to geometry to information, it's really a quest to understand what reality is at its deepest level. Is gravity one of the fundamental pillars holding up the universe? Or is it just a kind of illusion, something that emerges from the statistical dance of information and entropy? That's the question that keeps physicists up at night, and they're still searching for the answer.